Okay, and we saw how to define Gaussian processes and how to fit the Gaussian processes to data. In today's lecture, we're going to look at several interesting, or what I consider to be interesting, applications of Gaussian processes in different areas of statistics. So the topics that I'd like to cover today, which are these applications. The first topic we're going to cover is Gaussian process quadrature. Quadrature is a numerical method, but it turns out that you can also approach it from a Bayesian perspective by using Gaussian processes. So we'll see how to do that, and it follows directly from what we have learned about Gaussian processes. The next topic we're going to talk about is the topic of the statistical inverse problem using surrogate models. And we're going to use Gaussian processes to construct these model surrogates. I'll explain what that is in just a moment. And then at the very end, and I'm not going to go into details, but I'll show you some current research from my research group on some physics-informed spatial modeling. Where we construct covariance functions that enforce certain types of boundary constraints. So this is one type of covariance structure that is non-stationary, that results in a non-stationary Gaussian process. Great. So the first topic will be Gaussian process quadrature. And how many of you have seen or learned about quadrature methods before, such as the trapezoidal rule, for instance, or other quadrature methods? I can see several of you nodding. So you've probably seen this topic before, but I'm going to show you how to use Gaussian processes for this to do something that is, as some people call, uncertainty-aware numerical methods. So in numerical analysis, there is a large area on how to understand local and global truncation errors, of course, and an approximation error for quadrature, for example. And one way that we could try to capture an error that can be interpreted somewhat similarly is by using a Bayesian approach. And this is how it's done. It's kind of a fun application of Gaussian processes. So Gaussian process quadrature, or it's sometimes called also Bayesian quadrature, treats numerical integration as an inference problem. All right, so the goal of Gaussian process quadrature is to estimate a definite integral which I'm going to call I, the integral from a to b on the real line of this function g of t with respect to t. And g here is a function that has a known functional form. In other words, we can write down g, but we cannot integrate it. So we wish to approximate this definite integral when we can find its antiderivative. And so what we will do, one approach for this goal is numerical quadrature. And as I see, a number of you are already familiar with this topic. Essentially what it does is it transforms the continuous integral into a discrete weighted sum of function values sampled at specific points. So it uses the quadrature approximation. It looks like this. So it's going to be the sum I from 0 to n. N is the number of nodes or quadrature points of g of ti weighted by these weights wi. Ti are going to be these quadrature nodes. And they're the specific locations on the interval 0, 1, AB, where the function is evaluated. And then the second ingredient here are these quadrature weights, wi. These are numerical coefficients that are assigned to each function value according to a specific rule. So you might have heard, for instance, of trapezoidal rule, Simpson's rule, or Gaussian. There's something called a Gaussian quadrature, which is somewhat related to the result you'll see here. And it essentially represents the width of the influence of that sample point in a way. So it can be shown that different quadrature rules can integrate certain polynomials exactly. However, for all other functions, there is typically some numerical error that we have to account for. So our goal is to try to do this approximation and the uncertainty quantification all in one step. So we're going to look at this approach of Gaussian process quadrature. And I'm just going to note down that, one of the supposed advantages then is that it isn't, in some sense, uncertainty aware. Approximation. That's one way of thinking about it. All right. So first, let's recognize that even though we know the functional form of this function g, so suppose it's a sine or some other function, we don't actually know its definite integral, I. So using a Bayesian perspective, we might consider taking I to be an unknown parameter or quantity that we're trying to estimate, and perhaps put a prior on I. Okay. But since I results from applying a linear transformation to G, so integration is a linear operator, and since G is actually simpler to model than I, a priori, we're actually going to put a Gaussian process prior on G, even if we technically know its functional form. And that enables us to write down a joint prior for the integral that is unknown and the function G. So let me summarize this. So a Bayesian, when they don't know something, they usually put this prior distribution on it, and they collect some data or some information. There are many different ways of defining data. You'll see in this example, we'll define data a little bit differently. And then we're going to update that prior distribution into posterior distribution on this integral I, which will give us both an approximation and some idea of the uncertainty we have about that approximation. So let's first define a prior in G because that's the easiest exercise. The reason it's the easiest exercise is because we know that G is a function and the Gaussian process is a prior model on functions, right? So it's a random function. And so, we can say something about M0, right? So for instance, as long as, M0 could be anything, you could set it to the zero function for all t, or you could set it to something else. You just can't set it to G because even though we know what G is, we need to be able to evaluate M continuously. So that's one thing that you have to be aware of. And then we're going to choose a covariance. And the covariance, as I'll mention in just a second, has to be integrable in closed form in order for us to be able to use this Gaussian process quadrature. And luckily, this will apply to squared exponential and Matern covariances. All right, so we'll start with this prior. And the mean and covariance are specified using our prior knowledge. We, of course, know how many times differentiable G is, so we probably choose a prior that has the same number of mean square derivatives, for example. So what does this imply for the prior on I? Well, another nice property of Gaussian processes is that if you know that the marginals are Gaussian. You can figure out what the joint distribution of those is. And so that's what we're going to do here. So we're going to have a joint model on G and on I. Now remember that I just lives on the real line, so it's one-dimensional. G is a function. So this is still going to be a Gaussian process. And then m of 0 is going to be this function of t. And the mean of I is just going to be the integral from a to b of m0. And this is why I was saying that you need to be able to integrate m0 in closed form. So it could be like the zero function if you like. It doesn't have to be too precise necessarily. You can certainly set it to something close to g, but that you can, whose integral you can in fact compute. Write it this way. Okay, now the variance of I is going to be this double integral of the covariance. And then the cross will look like this. So where I'm getting this from is from the previous lecture, the last result that we talked about, of Gaussian process updated with multivariate normal data and the linear transformation. So this is like that L this is like applying this integral is like applying that linear operator L from the previous lecture at ds. All right, so this is a joint prior. So although we know G, okay, we still put a prior on it, and that gives us a prior on I. All right, and so the goal, of course, when we do the prior modeling over here is that we need to know that we can integrate M and we can integrate C sufficiently many times. All right, so just like in the numerical case, we're going to have n evaluations of this function G at these discrete nodes.
I have a question. So is covariance function supposed to be a function of both t and s here?
Oh, yes. So in this case, the covariance function is a function, yes, of both t and s. So the covariance function is going to be a positive definite. In this case, actually, let's say positive semi-definite, because we need interpolation. And then going to from AB to AB into R. Was that your question?
In covariance matrix, should the first entry be a covariance function at tt or at ts?
Oh, I see what you mean. Yes, that's right. That's TS. Thank you very much. Yeah, I appreciate that. Thank you. Yeah, that's a typo. Excellent. So just like in quadrature, we're going to evaluate these quadrature the function g at these quadrature points. And we're going to condition this prior on those numerical observations of the function g. And then I will define this vector of nodes as T obs for observations, just to make a distinction clear between the T that I used here and then this T, so T1 to Tn. Okay. So note there is no observation error in this case because we are evaluating g of t exactly. All right, so what we can write down is the joint distribution of this vector of observations. I'm going to call that G of T obs. Again, I'm going to abuse notation slightly. So G of T obs is going to be an n-dimensional vector. And I'm going to define this jointly with the integral I, this definite integral I. Okay, and just as an aside, this notation G of evaluated at this vector of observations is G at T1 to G at Tn. Okay. And so the joint model for this is going to be normal, because now we're dealing with vectors, no longer dealing with functions. So this is a vector, this is a scalar. All right, so the mean for G of T obs, the observed quadrature values or quadrature points, that's m evaluated at T obs. So the mean function evaluated at each of the quadrature nodes. And then the mean for I is still that definite integral of m naught. Okay, and then the covariance is going to be defined similarly. So here, and in this case, it will be T observed, this vector, and T observed as the arguments of that first covariance, the covariance of G obs with itself. So it's a covariance of a vector. So it's this is a covariance matrix right here. It's just the notation is a little funny because the way that it is often done this way in the machine learning community when we talk about Gaussian processes. So it's not the optimal notation, but we will use it here. Okay. So, and we have an integral here from A to B of this covariance function, and this is with respect to the second argument. Then the cross covariance looks like this. Now we're going to integrate this covariance with respect to the first argument. And then the covariance of I, or the variance of I should say, is going to be this double integral, and it's going to be with respect to both inputs, dt and ds. There we go. All right, so now we have a joint model on our observations and our unknown. So we can now use properties of Gaussian processes to find the posterior distribution. Properties of multivariate normal. Random vectors. And this can be shown quite easily. We have the posterior distribution of I given G of T obs. So this vector of quadrature nodes is going to be univariate normal, and it's going to have this mean Mn and covariance matrix, or sorry, variance, it's going to be variance Cn, I apologize. Mn and Cn. Well, Mn is on the real line, and Cn is on the positive real line. There. And the formulas for these can also be found. This is a well-known result, but it can also be proved. So Mn is going to be this integral from A to B. Of the covariance with respect to the first argument, multiplied by the inverse of the covariance matrix at all the observation observed values here, and then multiplied by the vector of the data, which is these quadrature points. Okay. So the idea again is we can evaluate this integral, and obviously this inverse is tractable here, and then we can do this matrix multiplication easily. And therefore, this mean gives us a nice approximation of the integral. The variance is going to be a double integral of the covariance function with respect to each of the inputs minus this information gain term. I think I'm just going to maybe move it to the next line to make it fit. And this cross covariance term, which involves an integral with respect to the second argument of the covariance. All right, so the mean, the posterior mean, provides an approximation, which is what the quadrature rule gives us, of I. Okay. And the posterior variance provides some notion of uncertainty. That is related to the smoothness, so the prior covariance, the prior choices, and the number of nodes. So I'm going to pause here and ask if there are any questions. I know this was going a little bit fast, but just the idea is that we now have a posterior distribution over this integral. So something like this. So these are possible values of that definite integral. So let's put here I on this axis, and here's the density. And it's going to be normal, univariate normal. And so this is the posterior mean right here, Mn, and this gives us an approximation of I, of this definite integral. And then the variance, the square of Cn, the standard deviation of Cn here is going to be the distance from the mean to the inflection point in this distribution. So it's going to control the spread of this posterior distribution. In other words, when this number of quadrature points is small, typically you'll have a larger spread here. And if the number of quadrature points is large, you'll have a smaller spread. Yeah. And of course, you can show asymptotically that this posterior density will concentrate towards the true value of I asymptotically under certain assumptions, so which is a result that is analogous to the results from approximation theory, which we can use to show that other numerical quadrature methods also work. Are there any questions?
Yeah, if I may, is there any idea why Cn decreases with n?
Oh, yes. Let's see. Let me see if I can describe it here. Right. Let me think of a good way to answer this question, maybe throughout the class. But yeah, there is a computational way to show that it decreases, that the posterior distribution decreases with n. Oh, let me actually, I'll probably tell you now before I think I have a good explanation. Okay. So this here is the prior variance of I, right here, this first term, right? And this is what we call the information gain term, right here. A second, we're subtracting how much information is gained by each additional point. There is, in the third homework, there is one question where we talk about sequential updating. So you can rewrite this for certain covariances in closed form as a sequential update. So with each new point that you add, you subtract a little bit more from this prior covariance. If that explains it well. If I can think of something more, a more technical reason for this.
So it decreases, and then one has to show that it decreases to zero, actually.
Yes, that's correct. Yes.
And so this gain is like in Kalman filter, that when we add one extra observation, we can update by rank one or something like that.
Yes, that's exactly right. So this and the Kalman filter are in fact the same thing if you think of just adding a single point and then taking the posterior. If you're assimilating the quadrature points sequentially, you can think of updating a prior, conditioning on a single quadrature point, then taking the posterior and using that as a prior for the next iteration, and then updating again, conditional on the next point. That is exactly the Kalman filter. Yes. Yeah, that's a great question.
And maybe yet another question about this mean. Mn is actually weighted average of the true values of G related at T observation. So this is a very special way to calculate these weights, W, J, or whatever. If the observation points are regularly spaced, is there any idea how these weights behave, and if there is any pattern, how? So these weights are unaware of G. I would expect that probably we have to place more points where G changes rapidly and can do sparsely if G is in the regions where G doesn't change very fast.
That's correct. Yeah. So there are ways of there is also Bayesian sequential design, which is another application of Bayesian methods for design of experiments, as we call it, or simply where to place the next quadrature point. So you can certainly use this for Gaussian process quadrature. It's not my area of expertise, but I think people have done this exact thing, which is where they use Gaussian process quadrature, but then select the nodes adaptively based on the posterior distribution, the latest updated posterior distribution. Yeah. So I'll try to find some references on that. Yeah, I think I've seen work on this area in Bayesian adaptive design.
So basically, the good approach would be to try to decrease Cn as much as possible with every new point.
Yes, exactly. You would place, right. And the way to do it is typically to place your next observation in a region of large posterior uncertainty. Yeah. So that would be, yeah, like a maximum entropy design or something along these lines.
Yeah, thank you.
Thank you. Great questions. And then let me show you some code on how to do Gaussian process, just showing you how Gaussian process quadrature looks. In the code that I provided in GitHub, I actually have a legend here so you can see what all the different colors mean, but I removed it for this demonstration because it was getting in the way of the plots. So basically we have a sine function in red, and we wish to integrate it from 0 to pi. So the true value of this definite integral is 2. So if we only use 3 quadrature nodes, the nodes are shown here as red dots. So as you can see, the blue line here, the dark blue line, this is the posterior mean. This is the posterior mean over G, not over I. So what I showed you was the posterior mean for the integral. And that would be this GP estimate here. This is the value of MN right here, 1.6856. And I didn't write down what CN was, but the equivalent distribution over G looks like this, though I didn't write it down, but you can actually use that same formulation that I used to write that down. And then these gray bands would be twice the pointwise variance in each direction for this Gaussian process. And as you can see, we're doing interpolation. We're assuming that specific point, so we don't have any kind of noise, and so this uncertainty shrinks to 0 when you get closer and closer to the point. Okay, and then as you increase the number of quadrature points from 3 to 4, suddenly your uncertainty decreases. I'll update the code to include the GP, the variance, the posterior variance of I, as well as the actual mean, but you'll see that the variance will shrink, and then it will shrink further as you add more and more quadrature points. Okay, so that's one application of Gaussian processes that's kind of fun. While you look at... Oh, yes, of course.
May I ask in this? Yeah. And how does it improve the standard quadrature, like with trapezoid?
Yes. So one of the ways that one of the reasons people argue for using this kind of Bayesian quadrature method is that it does provide you some of these uncertainty estimates. And there is some work on relating uncertainty estimates that you get from Bayesian quadrature methods, indeed many Bayesian numerical methods, to, for instance, like global truncation error and those errors that, have been studied for so many years in numerical analysis. So the idea is that this is, in some sense, uncertainty-aware method. So automatically you get both the approximation, but you also have the variation. And I will update the code to add both MN and CN, so you can see that the posterior variance of I also decreases with N.
And this mean also depends on the variance kernel that we are using. So this is probably the standard one, the quadrature exponential.
Yes,
one.
Squared exponential, exactly, yes.
Squared
This is the one that I use. Yeah, squared exponential, but you can use Matern because there are results, like somebody has integrated the Matern covariance, so you can still use it for this. As long as you can integrate these covariances in closed form, then you can use them. Thank you very much. Yeah. So just a few comments before we finish this particular topic. The first comment is that this is only one of many different versions of Bayesian numerical methods. It's kind of a controversial area because obviously numerical analysis and approximation theory are very old subjects that there's, many, many years of research behind them. People understand them very well. The Bayesian versions have certain connections to numerical analysis, to approximation theory. And they can sometimes be more convenient in certain situations when we want to track this uncertainty, and we want to incorporate this uncertainty into the inverse problem, which I'm going to show you in the next example. So there are some places where doing this kind of Bayesian version of the numerical methods is convenient. There are also things like Bayesian optimization, which is another type of uncertainty-aware numerical method. So it's using similar principles, but I won't have time to look through it today. There are also Bayesian version of differential equation solvers. So I actually worked on one during my PhD thesis. It was a fun project to try to essentially take the idea of using like an Euler method or one step ahead explicit numerical solver and turn that into a Gaussian process ODE solver. I have a student also who is working on a Bayesian or probabilistic version of the finite element method, which is a lot more complicated, but also very interesting because, again, you have this way of trading off formally the uncertainty that you get by reducing or increasing the coarseness of the finite element mesh. And that's something that can really help when you're doing like multi-level modeling or if you just want to spend less computational resources performing a task, doing prediction, but you also want to know what is the consequence of doing that in terms of uncertainty. So there's a whole area of this, and the area is called probabilistic numerics. So you can, if you Google this probabilistic numerics, in fact, there's a website, I don't know if it's being updated. I believe it's probabilistic numerics.org. I think that's the website. So you can have a look at all the different Gaussian process-based, most of these are Gaussian process-based methods. All right, so let's talk next about statistical inverse problems and how to use Gaussian process as surrogates. All right. So a little bit of terminology. The forward problem or the forward model it is the task of predicting, giving some inputs, the behavior of a system. And the type of inputs might be, for example, some maybe physical parameters or biological parameters. Some initial conditions or initial states of a system. There are many different examples. So for instance, if you have a model of disease spread, you might need things like the rate at which people transmit the disease, right? You need to know the rate at which the people recover from the disease, et cetera. So all those parameters. And you also need initial states. You need to know how many people are originally sick in order to be able to predict the behavior of the system. Okay, and this typically involves very time-intensive computation, such as solving a large-scale PDE model. So as an example, let me give you one example of so-called nano indentation for material science. So in material science, there's an important question of trying to understand how a material will respond to a particular force being applied and what the displacement will look like. For instance, if you poke an object into a metal, right? So we have this kind of machine that will, it's called a nano indenter, that will take a diamond-tipped indenter, and it'll just kind of press it into the material surface. And as you press it into the material surface, there's a machine that measures the displacement of the material around the indenter. Okay, so this is how data is collected. We haven't talked about data yet, but actually we do have a model for how this material will react to the penetration of the nanoindenter. So this model is a constitutive model of deformation. And I have collaborators that come up with these models. They encode physical laws, they write down these partial differential equations, and then they use a finite element numerical method to solve the system of equations. And here you can see in this picture, I can't make it larger. There we go. As you can see here, the amount of displacement that you get in different locations, right? Around, this is where the indentation site is, right? So this takes a long time, potentially, depending on how fine this discretization mesh is. And sometimes these models, not this particular one, but models of, for instance, climate models or other deformation models, can take on the order of days or weeks on a supercomputer to run. So these are not trivial, but if you input the material properties into this model, you'll get exactly the behavior that you expect to see, which is the deformation behavior. And this, solving the system of PDEs, is what we call the. Okay. And then there's the inverse problem, or this, let's call it the statistical inverse problem, just to be clear. And you can probably guess what this pertains to. So statistical inverse problem is given some measurements or observations of the system. We want to recover the values of the input parameters, and also at the same time quantify uncertainty from all sources. All right, so this is what we call the statistical inverse problem. One example of the statistical inverse problem, well, one example clearly is how to recover the material properties from a nanoindentation experiment. So, we might measure the displacement away from the nanoindenter. It actually comes in the form of this kind of loading and unloading curve. And then we want to, based on that, try to understand what were the material properties that are most likely given the data we observed. But another example of a statistical inverse problem is, of course, Gaussian process regression, where we observe what we wish to recover an unknown function based on some observations. So statistical inverse problems can be quite simple, like Gaussian process regression, or they can be quite complex, like this nanoindentation problem. So in practice, in fact, we typically want to constrain our inference with these more complex physical models rather than, just doing a Gaussian process regression, which will tell us something about the behavior of the underlying function, but perhaps that function is not going to necessarily obey some of the physical laws that we might be interested in. So before I introduce surrogates, I'd like to in hierarchical model. and I'm going to call it BHM for short. If any of you are also interested in any of this material, please let me know. I have some really nice references for all of these topics that I'm happy to share with you. So many models have a hierarchical or deep structure, and Bayesian hierarchical models are a multi-level statistical model connected by conditioning. All right, so here is an example with 3 layers. But you can think of, the likelihood being based on some intermediate layer of uncertainty and then another layer further down, which could be the prior. So here is an example. And the example is the top layer might be a likelihood. And suppose, for example, that, we wish to model some. So suppose that this data that we observe, these outcomes are independently distributed and comes from some model, which has this probability density function. And it depends on theta I, which are the group-wise parameters. So I is the group index. And J is the individual index. So how many, so the index of the individuals in the ith group, that should be I, not J. So something like this, where, we have the parameters vary by group, but not by individual, but we have different outcomes for each individual. So any kind of medical layer might be a model for theta. This could be a prior, or it could be what we call a random effect structure. So maybe the theta i's kind of vary independently around some other parameter. Let's call it eta. This is just an example. You can have many different ways of defining this kind of hierarchical model. And then the final layer might be a prior on eta. So for example, you might say that eta follows this prior model with this density. Typically, we use what are called directed acyclic graph diagrams to describe this kind of dependence. So I will briefly draw one for you. So I'm going to use rectangles to denote the observed values. So we're going to y1, 2, dot, 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 y1 and 1, and then we're going to have this for each of the k groups. This is yk1, yk2, dot, 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 yk, nk. And so all of these are conditionally independent. But they all depend on the individual theta I. So these guys are all informed by this unobserved parameter, theta 1. And these are all informed by this parameter, theta k. Okay, and now the second layer, so this is the first layer. This is your likelihood. And then the second layer would be we want to connect all of these thetas together with this parameter eta. This could be like some kind of center, or maybe all these theta i's are distributed around eta or something like that. So this is our second layer. And then we have a prior in eta, which is the prior layer. Okay, so the arrows here indicate the direction of conditional dependence. So as you can see, the y's depend on eta only through the theta i's. So they don't directly depend on eta. And this is one example how we can pool data together to try to estimate something that's related to an entire population that is heterogeneous like this. Are there any questions? This is just a simple example. Now, if we want to, what we're going to have to do is find a posterior distribution over these unknown parameters, the eta and the theta i's, given the data. So the posterior distribution has the following density for this specific model, of course, f of eta. So eta is the central parameter that's probably of most interest. Theta 1 through theta k, these are probably nuisance parameters in most cases. In other words, we're not necessarily directly interested in these theta 1 through theta k, but we still have to estimate them when we fit the model to data. And the data that we observe, which is yij for I 1 to k and j 1 to ni. And so this is going to be proportional to the likelihood times the prior, but of course the likelihood now has two layers, or you can think of the prior having multiple layers. It all depends on the model that you're considering how you would interpret it. But here's the likelihood. And then the likelihood will depend on the theta i's only. It doesn't depend on eta, because it only depends on eta through the thetas, as we saw in our diagram. And this is the likelihood. And of course, we can write this out in product form because we have independence between the yij's, but I'm not going to do it here in the interest of time. Then the middle layer is theta 1 through theta k, given eta, so this intermediate model. Middle or misspelled middle. And then the last part, the last factor here is the prior density. And it can be shown, and I of course mentioned that this product is proportional to the posterior distribution, and the posterior distribution is how we do inference. So you can take the posterior mean as being a good estimator of eta, or the theta i's, and then you can take the posterior spread as being some notion of uncertainty. Okay, now of course, typically we cannot evaluate important functionals of the posterior, like the posterior mean, posterior quantiles, in closed form for most models. So we use Markov chain Monte Carlo, which we obviously will not have time to cover in this class, but these are stochastic methods where you form a Markov chain in such a way, constructed in such a way that its stationary distribution equals the posterior distribution. So once you do that and you find that your Markov chain has converged hopefully, to the stationary distribution, you now have an approximate sample from that posterior distribution, and you can use that to find Monte Carlo estimates of the mean, the median, things you can use for estimators, and also quantiles, which you can use to kind of gauge how diffuse that distribution is. And you can do uncertainty quantification. You can find credible intervals, things like this. So this is how we do inference for multi-layer or Bayesian hierarchical models. All right, so are there any questions about Bayesian hierarchical models? Just have a few more minutes to show you surrogate modeling. All right, so let's go to surrogate modeling. Actually, I will give you a reference for this Markov chain Monte Carlo and Bayesian hierarchical models. The Gelman et al., it's a famous book by Andrew Gelman, who is a professor at Columbia of statistics, and his book is called Bayesian Data Analysis. It's a very practical book. Okay, there we go. It's a very practical textbook, and it contains some nice information about Markov chain Monte Carlo and Bayesian hierarchical and Bayesian inference in general. I highly recommend this book. I use it when I teach Bayesian statistics to graduate students. All right, so let's talk about now these surrogate models. For inference. Let's consider another example here. The following data generating mechanism. Suppose that I somehow was able to summarize my loading and loading curve for my nano indentation experiments into a univariate outcome y. You can do this for multivariate case, but we're not going to talk about it here. For simplicity, we assume we have univariate data here, and each I represents the index of which indentation it is. So we have multiple indentation. You take this indenter and you poke the material several times. So there's that constitutive model that I mentioned to you earlier, M, which is very expensive to evaluate. And we evaluate it at this parameter value. This is the true unknown parameters. These are the material properties in this case, for this example. Okay, we're going to assume there's some additive error. The error doesn't have to be additive, nor does it have to be Gaussian. I'm just giving you this as an example to make things simple. Okay, so this constitutive model is a very expensive forward model. So like I said, it might take days or weeks to evaluate for a single theta value. So whether you're using, optimization to solve the inverse problem, or you're using MCMC, Bayesian inference to try to recover theta, okay, you're going to have to evaluate M at different values, a large number of different values of theta. And that's just not feasible because the model is so computationally expensive. All right, so what we're going to do is we are going to make a model of the model. So we're going to take M and we're going to essentially interpolate it by a Gaussian process. Okay, and that's going to form the second layer of our Bayesian hierarchical model, because I also want to take into account the uncertainty of that in that quadrature, basically, not quadrature, sorry, the interpolation. Yeah, in the interpolation. Okay, so what do we do? So we need, because I should summarize that. So we need to interrogate meaning evaluate m repeatedly for different or arbitrary theta, we create a so-called surrogate model. Based on a finite number of model evaluations, really input-output pairs. So I'm going to now remove the dependence on t from my notation just to make things simpler. Typically, when you interrogate these models, you interrogate at whichever t values you need, whichever time or spatial locations you need. So we typically don't have to worry too much about that. It's really theta that is what we struggle to evaluate at m at. So m of theta, j from 1 to m. So as you can see, that dependence on t is gone now, because in principle we can, m is usually some really vector, really fine grid of t's or something like that. And t here is going to be t1 to tn. Okay. Oh, sorry, I didn't. I actually omitted t, sorry. There we go. Okay, all right. So what we do is we wish to construct a statistical model of the too expensive model that tracks uncertainty between the training data and locations. That also keeps track of uncertainty between training data locations. These input-output pairs can be thought of as training data for the surrogate model. Okay, and so an example of, we could write a statistical model that looks like this. So this function m, okay, I probably shouldn't have called it m, because, oh well, because I use m for the mean, but okay, it's done now. Theta 1, m theta 1 to m theta m. So given these training observations, we want to have a model for m, the function m itself, that we can use in that second layer of the hierarchical model. So we achieve this using Gaussian process regression. Okay, by putting a GP prior on m as a function of theta. So m is going to be a Gaussian process with mean function m0 and covariance function c0. And here m0 is going to be a function from the parameter space, which I'm going to call capital theta to the real line. And then c is going to be this positive semi-definite bilinear covariance function. Okay. So this is what m and c are. Notice that I'm not defining m and c in terms of t, in terms of the spatial input here. I'm using theta as the input. So theta is the parameter value, right? I'm trying to evaluate the model at different parameter locations. Okay. And so the posterior which is going to be exactly this function right here that we need for a middle layer or our Bayesian hierarchical model. The posterior distribution looks like this: m given m theta 1 to m theta n. This is the training data that we have. Okay, wait, m, how is m? Okay, is going to be a Gaussian process with some posterior mean mn and posterior covariance n. Okay, and then they have the usual form. So theta obs will be a vector here from theta 1 to theta m. And then the mean of theta, that's some predicted and observed location theta, prediction location is going to be C0 at theta, theta obs. C0, theta obs, theta obs. Inverse, again, we're observing the model exactly. There is no measurement error here, which is why this looks a little bit different than, the posterior mean that we saw in the previous lecture, because that one had observation error built into it, and in this case, observation error has zero variance. Maybe theta, theta star. Let's put this theta, theta star minus this Kalman gain. So we have the prior covariance minus the Kalman gain. And so here is the posterior distribution for that. And so now we have this middle layer of our Bayesian hierarchical model. Which now looks like this. Oh. So finally, this is what we have. We have a posterior distribution over our unknown theta and our unknown model at the true value of theta, which we also don't know. So we condition on the actual observations, theta 1 through theta n, but we also want to condition on these training observations. Okay, and so that's going to be proportional to the likelihood, which is the usual multivariate normal in this case, because we assumed an additive model with multivariate normal noise. So this is our likelihood. And then we have a Gaussian process posterior, which we just calculated. This is going to be, in our case now, multivariate normal, right? Or in fact, univariate normal, because m theta is a scalar in our assumed model. And then we have our prior on theta, which could be really anything. So now, to solve the statistical inverse problem, we say use Markov chain Monte Carlo to sample from this density, or the distribution with this density. And thus we can do Bayesian inference. Are there any questions? I know this has gone a little quickly. I can also show you some few slides with some results for that nano indentation data. The model is a little bit more complicated because we assume that each indentation has some spatial, a spatially varying component, but essentially this is what you obtain. These are over 3 different material properties. These are components of theta. So theta is not one-dimensional. In this case, it's 3-dimensional. And as you can see, we can have a posterior distribution over these 3 material properties, as you can see here. So please ignore this plot here. This is for something else. This is the posterior distribution over theta. Now, I provided you a posterior over theta and m, but you can actually marginalize over m quite easily using Monte Carlo. Okay. This is from a simulation, so the blue lines here are the true values of the parameters, so you can see we were sort of able to recover them relatively well in a data poor scenario. Yes, there's a question. Yes, please go ahead and ask.
Yeah, thank you. I wanted to ask, so original model also had a certain error, but we do not account for it because we just, our target is just approximation of model, or do we need to account for original model error?
Physical model, meaning there might be some missing physics, right, in this model? Is that correct?
Yeah, so there was the original model that yi equals
Yes.
this model and plus error, and that error is not accounted in this case.
Oh, so let me show you where it actually comes in through. So this this is how we construct the likelihood, right? So from this specification, we know that yi is going to be normally distributed with mean m and variance sigma squared. And so that comes in through the likelihood right here. So this component, I know I've gone through this relatively quickly, so it's hard to see that, but this is where the observation error comes through. So this is this normal distribution. Yeah, great question. Thank you. Any other questions? Okay, so that's kind of the interesting, another interesting applications of Gaussian processes. And then I don't have much more to write, but I do want to talk about physics-informed Gaussian processes. This is kind of a hot topic right now. It encompasses a lot of different things, some of which I wouldn't really call physics-informed, but there are some specific situations where you can design Gaussian processes to have certain properties that maybe match the properties of your interest, like of your system that you're interested in. So, you know, to think of Gaussian process-based spatial models that incorporate, for instance, some boundary constraints that you know are occurring. I'll give you an example in a second. This is just one type of non-stationarity. So you can choose a covariant structure that can help you in this task. And the question is, how can you construct such covariance functions where you want to encode some physical constraints into the prior directly? So I'm going to give you some references. I have some recent work with one of the students in my group who came up with a strategy to construct covariance functions that obey boundary constraints. So I'm going to give you the archive link for the preprint. That paper has some really nice pictures, so I'm actually going to show you some, and then one application. So this is where the preprint is, so you can have a look at what I'm going to show you. So here is a picture from that paper. Excuse me. So first, let's have a look at this right-hand panel right here. So we have a disk, a unit disk, And we want to define a Gaussian process that behaves in a specific way, but in terms of smoothness, etc. So anything like a squared exponential covariance is fine for us. But the one thing we do want in addition is we want to make sure that this Gaussian process with probability 1 attains these boundary constraints. This is a boundary constraint on the derivative. I apologize, on the state. And so one way to do this is to construct a covariance structure that has this property. I'll show you how to do that in a moment. So we want to enforce the constraint to this function in red, but we want the Gaussian process to behave normally otherwise, away from the boundaries. So these are two samples, two realizations from a Gaussian process with such a covariance. As you can see, the boundary stays the same, nothing changes, but what does change is what the process is doing, or the realizations of the process are doing inside the boundary, right? And it's the same for this particular plot. So the top and the bottom rows are two different samples from a Gaussian process. Now, this Gaussian process has constraints. One constraint on this side of the boundary along the derivative space. Okay, so derivative with respect to x1 here. This is this dimension right here. And then we have a derivative at this side of the boundary in this space. So that is the state space plus the derivative in the x1 direction. So you can see that you can constrain these Gaussian processes to follow some linear boundary constraints in many different spaces. And you can still see that these are still Gaussian processes. So all those Bayesian updating and Gaussian process regression results we talked about still hold. So one example of why you would need something like this is, again, in material science. So the picture here that you see shows you a tensile strength test. So this is a machine that pulls apart these specimens. They're shaped kind of like a dog bone, and they're made of usually some kind of a metal. And so this machine grips the top edge and the bottom edge, and then it pulls them apart slowly. There's also some spray paint applied to these specimens. So there's a camera that measures the displacement of all the little splotches of spray paint and tells you exactly then what the displacement is at each location, from each original location. And so this, what you see here in these colors here, are the displacements along the original dog bone. And so we actually know the force at which this machine is pulling this dog bone apart. So we actually know the vertical and the vertical displacement on the top edge and the bottom edge. And so if we want to use a Gaussian process regression model to try to recover the displacement field across this dog bone, which helps us to understand the strain field for this model, for this particular material, then we want to be able to constrain both the top edge and the bottom edge to have exactly that displacement, which we know the machine is imparting on the sample. And so this is one of the application of this kind of boundary constraint Gaussian processes. Are there any questions? If there are no immediate questions, I will end the lecture here. I would like to thank the organizers and the students. Thank you all very much. Slava Ukraini. Thank you for this opportunity.